Welcome, everyone. This is the fourth annual Graduate Student Research Conference co-organized with NISS, the National Institute of Statistical Sciences. My name is David Matteson. I'm the new NISS director, and I'm a professor of statistics and data science at Cornell University. We're really excited about today's program, but I do want to emphasize that everything today came together because of a network of graduate student volunteers. This conference is both for graduate students and by graduate students, and the NISS staff is here to support those efforts. We're really excited about today's program. We've got a large set of presentations by graduate students, some career panels that span academia, industry, and government, and some really special keynote talks both today and tomorrow. With that, today's program, we're looking at new methods and applications in biostatistics, bioinformatics, and network analysis. Later in the afternoon, recent developments in high dimensional data analysis, non-parametric statistics, and uncertainty quantification. I want to say a couple things just about NISS before we get going with today's event. So NISS is an independent nonprofit research organization. NISS's history is that about 30 years ago, it was founded by our largest professional societies at the time, the American Statistical Association, the Institute of Mathematical Statistics, and the International Biometric Society. So those professional societies got together with other institutions, particularly the Triangle Universities and the state of North Carolina at the time, to found a research institute that tries to harness the profession of statistics. As new director, I try to bring in the fields of data science and now also artificial intelligence into the activities that we do. Cross-disciplinary and cross-sector research is the key distinction for the National Institute of Statistical Sciences. The Graduate Student Network is part of a broader affiliate committee, and the affiliate committee is charged with making those links across sectors and serving each one of the individual sectors the best it can. So that includes across industry, academia, and government and national labs. As new director, I'm working to found the new NISS Collaboratory to inspire and seed even more collaborations. Some of my strategic priorities are gaining a better understanding of the intersection of AI and statistics, highlighting the success and importance of collaborative data science, engaging more in biological applications through machine learning methods, enhancing the data visualization and design history and strengths of NISS, continuing our training, validation, and consulting work, and to help found a new researchers network, which will be seeded by this graduate student network. I also do a lot of work outside of NISS, including editing a new journal called Data Science and Science, which is a ASA journal publication as well. And it's free to submit, and also it's open access. So check it out if it's a good fit for your work. One of the most important research programs that NISS has since 2019 is the Statistics Serving Society program. We call this the Ingram Occam Forums, in memory of one of the founders of NISS. So the key here is that the power and beauty of statistics is what unites us, but can also enable further change in society through not just statistics, but also data science and now AI. So this is a broad community. Everything that NISS does is largely volunteer driven. This is also a community that you can become part of too. So a brief history of some of the things we've done, just to highlight some of these outward facing research programs. We had our gun violence as our founding forum in 2019, but we had a second part of that just this last week, gun violence part 2. Another upcoming program, which will start in 2025, is a joint venture between NISS and IMSI, the National Science Foundation funded Mathematics and Science Institute in the Chicago area. It'll study data science at the intersection of public and environmental health. These are long programs. These are programs that span at least a whole semester, and they each strive to have at least one or more in-person events, but a lot of virtual and hybrid events to complement that. There's currently an open forum that's continuing to this day on police use of force that was started in 2021, and we had an in-person event this last fall. So there's an open call for proposals. This is on a continuum, but we start to review these every 6 months. So if you've help identify a new area of high impact societal problems that you think statistics can help solve, please consider forming a working group and put together a proposal. You're not too young to do this. I think that having junior people, new researchers get involved early on in the process is a key to having them have strong energy and strong representation throughout the whole program. Finally, I'm striving to get additional theme semester programming going. So one of my key roles as director is to secure institutional support for all the activities that we want to do across NISS, and that's to enable the things you want to do. So my hope is that we do, as a community, establish theme semesters that have connections across our units, but that also have activities that you can help lead locally. So with that, I'm going to introduce Piamo Liu. She is the chair of the steering committee for the Graduate Student Network, and she has a few announcements as we get started. Piamo.
Hi, everyone. Thanks, David, for such a wonderful introduction to NISS and our conference. We appreciate your support. Very quickly, I want to use this opportunity to thank our keynote speakers, presenters, panelists, volunteers, and NISS to make our conference a great learning opportunity possible. I have two announcements to make. One, our first keynote talk will be delivered by Professor Razia Nabi from Emory instead due to a scheduling change in our agenda. Professor Miguel Hernan will deliver the second keynote talk tomorrow. Sorry about any inconvenience and this will cause. Second announcement, if you are joining the conference not as a presenter or speaker, please use Q&A or chat to interact with other attendees and speakers of the conference. Without further ado, let's move on to the first session of our conference today. Thank you.
Okay, so let's jump to the oral presentation. So the first speaker is Chris Kam coming from Yale University, and I will use the official time app from Zoom to give a 18 minutes heads up. So in total you have 20 minutes including Q&A. So I will have a 18 minutes heads up and also 20 minutes. Yeah, Chris, please pull up your slides and then you can feel free to go ahead.
Right.
Can you see the timer?
Yes, I can.
Cool.
Right. Is that looking good?
Yeah, and sorry, I need to, and his talk is about translating between neuroimaging effect sizes and classification accuracy. Yeah.
All right, thank you so much. And thank you so much to the organizers for putting all this together. I'm really happy to start things off. Yeah, so I am a third-year graduate student at Yale University, and I work with neuroimaging data to apply statistics to see how we can better use brain scans to understand things like psychiatric illnesses.
Chris, you actually need to switch to the presenter mode.
Oh, okay. Let's see. Let's see if I can... How is that working now? Is that better?
Yes, that's better. Thank you.
All right, so we'll get started. All right, so neuroimaging data offers the promise of improving our diagnosis and treatment of psychiatric illnesses by giving us a window into the brain. However, so far we've been largely unsuccessful in identifying clinically useful biomarkers for the brain. One of the key obstacles to scientific discovery in neuroimaging may be low statistical power. Neuroimaging data is noisy and high-dimensional, and this results in low effect sizes. Due to the relationship between power, sample size, and effect size, many neuroimaging studies are underpowered without the infeasibly large sample sizes necessary to detect these associations. This can lead to a high proportion of published false positives. Researchers have increasingly turned to machine learning as a way to extract meaningful features from complex neuroimaging data and classify individuals into clinically useful groups. These features could include gray matter volumes from structural MRI, connection strengths between regions from tractography, activity from functional MRI, or electrical time series from electroencephalography. These diverse sources of data, each of which can produce thousands of different features, present a great opportunity for machine learning applications. However, while classifiers may be able to combine these features in different ways to best distinguish distinct groups, model performance is ultimately limited by the effect sizes of the underlying features. The relationship between these two things, effect sizes and classifier model performance, is key to understanding how we can successfully apply machine learning to interpret neuroimaging data. To answer these questions, we developed a framework for converting between effect sizes and classification accuracy across different data conditions, such as effect size, how many features you have, and what covariance exists between those features. Rather than measuring the performance of different classifier models, we wanted to understand the upper bound of classification accuracy given those conditions. In other words, if you have a set of features with some difference between two groups, what is the best that any classifier could possibly do? We did this by measuring the overlap of the distributions from which these features are sampled. Let's say we sample one feature from two Gaussian distributions with a Cohen's d effect size of 2. If 85% of each distribution lies on either side of the threshold, the maximum accuracy any model could achieve would be 85%, because an optimal model would classify all of the samples below this point into one group and all of the samples above this point into the other group. The overlap, and thus the maximum classification accuracy, can be easily calculated if we know the probability density functions of the distributions. The density function describes the probability that a sample will have a particular value. So this is the function for the normal distribution. Similarly, the integral of this is the cumulative distribution function, which describes the probability that a sample will fall within a range of values. By plugging in the midpoint between these distributions as x, we can determine the maximum proportion of random samples which could be correctly classified in each group. This means that as long as we know the effect size d, we can determine the maximum classification accuracy of this population. The midpoint x is the Cohen's d times the standard deviation over 2, so that's just undoing the Cohen's d formula, and this is just the difference in the means. And the cumulative distribution of all values x less than this midpoint is then the cumulative density function phi of d sigma over 2. Okay, so what happens if we have multiple features? If the effect sizes are all equal, then an optimal classifier will just take the average of all the features for a given sample. So for our last question, we now have x bar as the average of all the features, and we want to know the probability that this average is less than or equal to that midpoint. We can solve this as a convolution using the central limit theorem. So this tells us that no matter what the initial distributions look like, if we average together values sampled from each of them, the resulting distribution's mean and variance will just be the average of the original mean and variance. When you take the square root of the mean variance, you get the sigma over the square root of the number of features. So now we just use this normal distribution as our probability density function from before. And if our features aren't independent and share covariance, now the mean remains the same, but our average variance is the average of the covariance matrix. So now that we have this framework, we can answer some interesting questions. The most obvious place to start is by looking at how the number of features affects accuracy. As you'd expect, at any given effect size, as you increase features, the accuracy improves, indicated by the lighter colors. However, with smaller effects, as are quite common in neuroimaging, the gains from added features become limited. Just to represent this another way, we can separate these lines out by effect size and look at how many features are required to reach 90% accuracy. So this ranges from 7 for a Cohen's d of 1 to 657 features for a Cohen's d of 0.1. However, these data represent an ideal scenario where all the features are completely independent and uncorrelated. In biological data, it's much more likely that a set of features would have some amount of covariance. So here's the same plot, but now with a Pearson's R of 0.3 correlation between all of the features. You can see on the right that even with a large effect size of 1, accuracy barely crosses 80%. Looking at this another way, here's accuracy as a function of correlation on the y-axis and effect size on the x-axis, with features fixed at 100. This makes the impact of covariance between the features quite clear. To validate these results, we can look at how they compare to an actual classifier model. Here we have the theoretical maximum accuracy on the x-axis and a naive Bayesian classifier model on the y-axis. As you can see, the model performance lines up perfectly with the theoretical maximum when given a large enough training set. To help contextualize these results, we can look at effect size distributions in neuroimaging data. Postdoc in my lab, Zhang, ran correlations on the 3,500 neuroimaging features from the UK Biobank Consortium. These include a range of structural and functional MRI measurements for thousands of participants. This plot shows the distribution of correlations between features, and this one shows the correlation between age and all features in the terms of Cohen's d. We looked at age first as a benchmark, as we're able to predict age with fairly high accuracy using neuroimaging data. We can then successively model the highest effect size features to measure how accuracy changes. So you can see the accuracy reaches 95% with just 32 features, with a mean effect size of 1 and an average correlation between them of 0.48. To summarize, we can use simulations and cumulative distribution functions to estimate an upper bound for classification accuracy given a set of effect sizes. We see that increasing feature count aids classification, but is unable to rescue really small effects. Covariance rapidly diminishes the effects of increasing features. And classifying populations on a single neuroimaging feature is unrealistic without really large effect sizes for that feature. But sets of high effect size features can make accurate classifications when combined optimally. Of course, these conclusions are already well established. We know that model parameters should be independent in order to have the greatest impact on performance. However, it's increasingly important to be able to assess this impact in real-world neuroimaging data. In that context, it appears that machine learning performance is severely limited by the strength of the underlying effects. In the future, we're developing simulations to model more complex nonlinear and interaction effects to better understand how this complexity might affect classification performance. Now, I'll say thank you so much for listening, and thank you to all of the people that have helped me with this work. And I'm happy to take any questions.
Thank you, Chris. Are there any other questions from the audience? If
Hi,
not,
Chris. This is Shihao. I'm faculty at University of North Carolina, and great talk. Quick question. So if you have multiple features and then like you do need to normalize them rather than otherwise the effect size are not, for example, under the same unit and then cannot directly harmonize, right?
Right. Yeah. So you would want to be using standardized effects or standardized features in practice. Because, yeah, like I was saying, the different features can come from really diverse sources. So you could be using such as the correlations between different features. If you were looking at functional connectivity, you could be looking at time series data. Yeah, you would see a really large range of the magnitudes. And so it would be really important to standardize that.
Okay, thank you.
Mhm.
Chris, can you see the questions from the chat? There is a question from the chat from Chalmers. And he asked for the neuroimaging features, are there possible regularization methods to handle the possible correlation between features?
Yeah, so I think that's kind of the big question that a lot of researchers in neuroimaging have been trying to tackle is what are the best methods, what are the best models for incorporating different neuroimaging data sets and kind of producing the optimal model. And that's really the question I'm trying to answer, kind of coming from the other way by using simulated data that's modeled in neuroimaging data, and then seeing what are the how can we best take advantage of those effects. So I don't have a simple answer to that. I mean, people have had success using deep learning methods, using SVM models, but it really depends on the exact neuroimaging data set that you're using, and the trade-off between how correlated your features are and what their effect sizes are. It's a good question.
Okay, thank you, Chris, for your great presentation. And then I think we can move to the last presenter. Let's welcome Wenlong Yang. He's from Penn State University, and his presentation title is Weighting-Based, Regression-Based, and Missing-Based Multiply Robust Estimators. And Wenlong, I think you are good to turn on your slides. Yeah.
Hi everyone, I'm Wenlong from Penn State University. Let me check. Okay. I'm very excited to share with you today a recent paper that I find very interesting and inspired my own research work. It was published on Bioinformatics in 2020. So basically, it shows that a class of weighting-based and regression-based multiply robust estimators in recent literature are actually special cases of double robust estimators that were proposed in the last century. Based on that observation, the authors proposed a new class of multiply robust estimators using model mixing procedures. First, I will give a preliminary including what motivates double robust estimations and what are the popular classes of double robust estimators. Then I will move forward to weighting-based and regression-based multiply robust estimators and explain why they are special cases of double robust estimators. Finally, I will explain how the authors come up with model mixing-based multiply robust estimators and briefly explain some theoretical properties. First thing first, the goal throughout my presentation is to estimate some population parameter, for example, the population mean of the outcome variable y. Suppose that we have an NIID sample where the covariates x are fully observed and the outcome y is only observed for the first m samples. We make two common assumptions here, including that y is missing at random and that for any value of x, there's always a positive probability that y is observed. We know that to estimate the population mean of y, if we simply take the sample average of observed values yi, that will lead to a biased estimate of mu because y is missing at random but not missing completely at random. Two popular approaches to tackling this problem includes inverse propensity weighting, which involves a propensity score model pi of x to predict the probability that y is observed given x values, and use the inverse propensity score to reweight each observed yi and take the sample average of weighted average of observed yi values as an estimate of mu. Another approach is outcome regression, which regress y over x, and then take the unweighted sample average of observed yi values and predicted y values if y is not observed, and use that unweighted average as the estimate of mu. Now here comes the question, which model should we use? Or let's make it more complicated. If there are multiple propensity score models and multiple outcome regression models, which model should we use? It's hard to answer because we don't know out of all those models, which one is correctly specified and which ones are not. So I I would be very happy if there's an estimator that combines all those candidate models and gives me consistent estimate as long as one of those models is correctly specified. Okay, so that is what double robust estimation and multiply robust estimation aims to achieve. If we use PN to denote sample average, then the outcome regression estimator and IPW estimator I just mentioned have this very nice and simple form here. A way to combine these two estimators is the augmented inverse probability weighted estimator, which constructs an augmentation term using the outcome estimator, and it can be written in two different forms. Let's take a look at the first line first. So if the pi of x, the propensity score model, is correctly specified, then this second term here will converge to 0. So the AIPW estimator will have the same probability limit as the IPW estimator and will be consistent. Similarly, conversely, if we have a correctly specified A of x model, then the second term on the second line here will converge to 0. So the AIPW estimator will converge to the true value, just like the outcome regression estimator, and it will be consistent. So now we have double robustness. If either the propensity score model is or the outcome regression model is correctly specified, then the AIPW estimator will be consistent. That gives us double guarantee because we don't need to know which of these models is correctly specified. In 1995, Rudnitsky and Robbins proposed another class of double robust estimators we call weighting based. So the weights are they're looking for weights inverse of pi2 of x as the way to reweight each observed yi values, and use the weighted average on the observed yi values as an estimator. The parameter delta of this propensity score is found by solving these estimating equations, which basically is matching the weighted average of T of x over the observed samples to the unweighted average on the total samples. If we combine the expression of the estimator and the estimating equation, we can write it in the form of an AIPW estimator. So again, we can using the previous conclusions, we know that this estimator is double robust, meaning that if either the pi2 of x is correctly specified or the a2 of x is correctly specified, then this DRIPW estimate will be a consistent estimate of mu. In 1999, another class of double robust estimators based on regression was proposed. It's more straightforward, so now we have a link function b, and we use zeta of x, which is a non-function, and inverse of pi2 of x as the covariates to predict y using x. Following standard OLS conclusions, we know the residuals y minus a2 of x and the covariates 1 over pi2 of x are uncorrelated. So that constructs our estimating function. If we combine this equation with the original expression, we can also write this DRRAG estimate in the form of an AIPW estimator. So it's also double robust, meaning that if either a2 of x or pi2 of x is correctly specified, then our estimate of mu will be consistent. Now let's move forward to multiply robust estimator. Recall that the goal is to find an estimate that is consistent as long as one of those many models for pi of x or a of x is correctly specified. Dr. Han and Dr. Wang in 2013 proposes a weighted average as their estimate, where the weights are found by solving this standard convex optimization problem. So the constraints are basically saying they sum up to 1, and the weighted average is observed samples from I equal 1 to m equals the unweighted average on the total sample I from 1 to n. Using Lagrange multiplier method, we can write the explicit form, the analytic solution for those Wi, which involve Lagrange multiplier rho here. And rho is solved by this final equation here, which is derived from the constraints on Wi. If we plug in the explicit form of Wi back into the expression of mu hat, we can compare it to the double robust estimator, and we realize that in the multiple robust estimator, the weights are actually also can be regarded as inverse propensity score model, which is a combination of different models and has the Lagrange multiplier rho as its model parameters. And the constraints on Wi can be expressed in terms of the model parameters delta. So we have the model, we have the estimating functions for delta here, which also matches the estimating functions for in the double robust estimator, which means now that we have established that the weighting-based multiply robust estimator is a special case of the double robust estimator. In 2013, Dr. Chan proposes a regression-based multiple robust estimator, which is a very natural extension of the double robust regression-based estimator. It uses many different models for propensity score and many different and inverse of many different models for the propensity score as the covariates to predict y using x. And so comparing to the double robust regression estimator, we now just have many different covariates instead of only 2 covariates. To conclude, the multiple robust weighting-based estimator is just to combine all those different models into a final propensity score model. And the regression-based multiple robust estimator is just to combine all those different candidate models into a final outcome regression model. A natural question to ask is, with all those flexible model mixing procedures, why don't we just use other model mixing methods instead of these very specially designed ways to combine these models? So that is why the authors of the paper I'm discussing today come up with the model mixing based multiply robust estimator. First, they combine the different candidate propensity score models into one final propensity score model using the procedures here. It looks complicated, but core idea is simple. It just divide the full data into 2 different portions, fit the models on the first portion, and evaluate those models using predictive likelihood on the second portion, and which model has better predictive performance receive a higher weight in the final combination, in the final combined model. And the lemma shows that if the lemma establish an upper bound for the predictive predictive risk of the final combined propensity score model. And they also combine the different candidate outcome regression models by similarly, we divide the data into 2 parts and fit the model in the first part and evaluate their predictive risk on the first part, on the second part of the data, and which model has lower predictive risk will have higher weights in the final model. And they also establish an upper bound for the final combined outcome regression model. Their final estimate of mu is an AIPW estimator, which combines the final propensity score model and final outcome regression model. And they also establish the consistency of their final estimate mu hat mix. Theorem 2 and theorem 3 shows the consistency of mu hat of mix and establish the asymptotic normality of such an estimate. I will skip the simulation studies here because, in my very personal opinion, it's the least interesting part of the paper. I believe the key takeaways of this paper is that weighting-based and regression-based multiple robust estimators proposed 10 years ago actually can be regarded as special cases of double robust estimators from last century. And based on this observation, we can use more model combination techniques to combine these models into final propensity score model and final outcome regression model, so we can skip the very intricate specifications of those final models in the double robust estimator. There are also some final thoughts here. For like, as we just see, the way that the authors proposes to combine these models, like the omega here, they have a very complicated form. But we also have so many choices for model mixing procedures. I believe we can use other more simpler model mixing procedures to construct a final model. And second thought is that model mixing or model selection, like among all those models, we are now trying to combine them into one model, but why don't we just choose the best model? When should we use model mixing and when should we turn to model selection? There's ongoing discussion on this topic. In my opinion, I feel that it depends on prior knowledge. If we believe that one of the models will outperform others very obviously, then maybe we should just do model selection instead of model mixing. The final thought is that what if Y is missing not at random? That complicates the issue because the missingness indicator and the Y itself is now correlated. And this is what I'm doing in my current research project. Here are the references. I guess that concludes my presentation. I'm happy to take any questions.
Hi, Wenlong. Thomas from the chat asked a question for the model mixing methods. Do you think AIC and BIC will be incorporated in model selection?
That's a great question. So far, the authors are doing model mixing instead of model selection. So they are using the final propensity score model, they are using this predictive likelihood, which has the form of a Bernoulli likelihood to evaluate the model performance. But I believe you can also use AIC or BIC to evaluate the models and build the model weights for each model based on AIC and BIC. I have tried that. It doesn't. In my simulations, it doesn't work so well. I don't know why. But I believe that is a direction that you can explore, right?
Yeah. Thank you for the answer. Are there any other questions from the audience?
Hi, Wenlong, great talk. And I have a quick question. So can you comment on moving this regression framework to a more black box machine learning, like using double machine learning? There's a kind of analog to that aspect as well, or not? For this
Sorry,
robot.
what is, I'm not very familiar with double machine learning. What is that?
So basically like moving beyond this this regression type of framework by replacing this estimation and prediction using some like for example machine learning algorithms.
Oh, I see.
Can we do that in parallel?
Yeah. So basically, we have shown that the multiply robust estimators can be achieved. Multiple robustness can be achieved by model mixing. So, like in a random forest, we are combining we are doing a model ensemble, and I believe that technique can also be applied here to combine these models.
Great, thank you.
Thank you for your question.
If there are no answers from the audience, Thank you, Wenlong, for a great presentation. I think we can move on to the third presenter, Zhang. She is from the Department of Computer Science and Statistics from University of Rhode Island, and her presentation title is about the power and sample size for evaluating spillover effects in networks with non-randomized interventions. And I think you are good to share your screen.
Okay, thank you.
Mm-hmm.
Can you guys see my screen?
Yeah.
Okay. I cannot make it bigger, so just hopefully this is fine. So thank you very much for the introduction, and thanks to GSN giving me this great opportunity for presenting my research. And my topic here is the power and small size for evaluating the spillover effects in the networks with non-randomized interventions. First of all, I want to thank our collaborators on this work, the Dr. Ashley Kanka, the Dr. Tim Fang, and other collaborators. Also, thanks for the funding from the NIH. So, this presentation will be split into these 5 sections, and the first one is the introduction. So, I want to first give some background information. The people who inject drugs stand for the PWID are embedded in the HIV or HCV risk networks, and the intervention for these networks often has a spillover effect, where the spillover effect is defined as occurred when one individual's exposure has effect on the outcome of another individual. So this PWID networks will have the spillover effect because of the interactions between the individuals, and each individual's inference site may be unique and not partitions network into the groups or clusters. There are different types of the possible interference site, such as the cluster level or 1-degree neighbors, or the 2-degree, or the entire networks. And the spillover effect, mathematically, it is different from the average causal effects that typically it ignores the spillover. And another definition for the nearest neighbors. In this work, the nearest neighbors refers to the first degree in the network, which is the individuals who has the direct connection to the index individual. For example, in this network, the red one, if this is the individual for the red one, then the nearest neighbors for this red one are these 4 origin nodes. So this is the definition of the nearest neighbors. The motivating study for this work is another study called the Transmission Reduction Intervention Project, which is TRIP. And this is a supermetric network-based study for the PWID population and their context in the ASINs from 2013 to 2015. The intervention here is the community alerts if the individual get community alerts about the HIV infection. And the outcome is HIV risk behaviors after 6 months. So at the baseline interview, this study has 277 participants, and 29 of them were alerted. After 6 months, the follow-up interview contains 216 participants, and 92 of them reported at least one risk behavior. So here, if we want to evaluate the spillover effect of the community alert on the HIV risk behavior, first, before we actually estimate the effects, we want to ensure that our study has the adequate statistical power to detect the spillover effect. This is critical. However, the existing simple and power analysis approaches usually focus on the overall effects in the cluster randomized trials of the IPW estimators, which is inverse probability weighting estimators with no spillover in the observational studies. Or they do have the approach to evaluate the powerful spillover effects, but it is in the two-stage randomized or the multi-level randomized design, which is typically not feasible for the sociometric network studies. So then it raises the question, is the network of these 260 nodes and 362 edges enough to detect a meaningful, statistically significant spillover effect? So this is a generalized research question will be, in the network-based non-randomized studies, how do the network design parameters, for example, the number of the components or nodes, the node degree, how these parameters affect the statistical power of evaluating the spillover effects? So in this study, we first conduct a simulation study to evaluate the impact of different parameters on the power of detecting the spillover effects using the inverse probability weighting, the IPW2 estimators. So the design parameters here include the number of components and number of nodes, also the node degree, and the transitivity, which is also known as the clustering coefficient, and the effect size. And the second objective for this research is to develop a closed form expression for calculating the power of detecting spillover effects in the sociometric network-based studies with non-randomized intervention. So then we move to the methods. First, we give some notations that we will use later. First, we let the I denote each participant, the participant indicator, and the AI and ZI are the binary treatment or binary exposure for the individual eye, and the vector of the covariates for the individual eye, respectively. And NI represent the set of the nearest neighbors, which we already defined before, the participants that share a link or share a connection with the individual eye. And the DI is a number, which is the degree of node I, or we can say it's the number of the nearest neighbors of individual eye. And the ANI is a vector of the baseline exposure for participants in the NI in this nearest neighbor set of individual eye. And the ZNI similarly is the vector of the baseline covariates for the participants in the nearest neighbor set NI. And we also define the GK as the components indicator. K is from 1 to M is the number of components in this network. And the SI is the representing the number of the exposed nearest neighbors of the individual eye. And the YI is the potential outcome of the individual eye if they receive the intervention AI. AI could be 1 or 0, it is binary, and their nearest neighbor receives a vector of interventions denoted by the ANI. And this capital YI is equal to the YI given the AI and ANI, which is observed outcome. And for the estimates, so first we define another parameter called alpha. We call it allocation strategy. It represents the probability. It represents the proportion of the nearest neighbors receiving the intervention, or we can say the probability of the nearest neighbors receiving the intervention. So the probability of the neighbors of individual eye is denoted as pi given ANI and alpha allocation alpha, and it will be alpha with the power of the sum of the ANI, which is the sum of the exposure for the nearest neighbor set, and given the y minus r, the probability of not receiving the intervention, and the power is the number of the nearest neighbors not receiving the intervention. And similarly, we have the probability of individual eye receiving the intervention is the pi AI given alpha is the probability of this individual eye receiving the intervention given the actual exposure they received. AI is equal to 1 or 0. This is just some very basic binomial probability equations. And we also define that pi given the probability of the given AI and ANI. So the individual eye receiving the intervention AI and the nearest neighbor site receiving the intervention ANI. the probability of this given the allocation strategy alpha is the product of the pi ANI given the alpha, and the pi AI given the alpha. It's just the product of the above two. And the population average potential outcome is defined as I showed here. So this is the average of all the potential outcomes for the total number of the individuals in this network, which is N. And once we have the population average potential outcome, then we can define the spillover effect, or we call it an indirect effect, under the specific allocation strategy alpha, which is alpha 1 and alpha 0. This is two different allocation strategies, and we assume that alpha 1 is larger than alpha 0. And the spillover effect will then be defined as the population average potential outcome given the individual not receiving the intervention. And the allocation strategy is alpha 1 minus the population average potential outcome given the individual not receiving the intervention, but the allocation strategy is alpha 0. So this is how we define the spillover effect. And sorry for typo here. This should be IE given the alpha 1, alpha 0. Okay, same. Okay, so before we actually conducted the simulation, we first have several assumptions for the spillover effect. This is also the assumptions for the IPW2 estimate we will use later to estimate the spillover effect. First is the nearest neighbor interference. So in these assumptions, we assume that the potential outcomes only depends on the exposure of the individual themselves and their nearest neighbors exposure, and the conditional exchangeability for the participant I, and also the conditional exchangeability for the neighbors, the nearest neighbor site and I. This conditional exchangeability assumptions is to ensure that the effect we finally observed is solely from the intervention, not from the difference between groups or between individuals. We also assume the treatment variance irrelevance is, we assume there's only one level of the treatment at one level of treatment. There's no variation of the different level of treatment, especially in this case. We only have the binary treatment, treated or not treated. And the positivity, we assume that the probability of the individual receiving any level of the treatment and their nearest neighbor site receiving any level of combined treatment vector are this probability are larger than 0, are positive for all possible AI, ANI, ZI, and ZNI. And we also have the stratified inference assumptions and reducible propensity score assumption. This is assumptions for this IPW2 estimator we will explain later. So recent methodology development allows for the inference set within the components defined as unique to each person. And here we introduce the nearest neighbor IPW2 estimator, which is proposed. The estimator we use is proposed by the Dr. Ting Li in her paper published in 2023. And when the partial inference assumption, which is assuming that the individual, the inference set is the whole cluster, whole component. This is the partial inference. Sometimes it doesn't hold. Sometimes the inference for the individual, even within one component, are unique. So we propose two IPW2 estimators where the inference set is the individual's nearest neighbors within the network instead of the whole component. And there are two types of the IPW estimator. The IPW1 is a novel application for the sociometric network-based studies settings, and IPW2 uses a generalized prevalence score, which is proposed by the Dr. Here 2016 with the weighted estimators instead of the stratified estimators. In our work in our simulation study and our work in the rest of this presentation, we use the IPW2 estimator. So the population average IPW2 estimator for the population average outcome is defined as I showed here. So the pi we already defined before, and the F2 is the frequency score, which represents the probability of the individual receiving the intervention AI and their nearest neighbor site receiving the vector, the number of nearest neighbors that are receiving the intervention. And here is how we define the estimate. So regarding the simulation procedure, first we need to generate the network. When we generate this network, we customize the number of components, number of nodes, every component size, the node degree, or the transitivity, depends on which type of simulation we were conducting. And then we will determine the non-hypothesis and the alternative hypothesis. Non-hypothesis here is there's no spillover effect. The IE is equal to 0. The alternative hypothesis is there's a non-zero spillover effect. The IE is not equal to 0 under the significance level of 0.05. And after we have the network and the hypothesis, we need to simulate the random variables and the potential outcome, the PO. So for the random variables, the exposure AI, we assume we just simulated from a Bernoulli distribution, gives the probability of this Bernoulli distribution is the logic function for the 0.7 minus 1.4 times CL, which is the covariance of the individual I. That's the random effect. These numbers are based on the regression results from the observed data from the tree network. And when we simulate the potential outcomes, we give another Bernoulli distribution, and given the probability is relative to the individual exposure and the proportion of exposed nearest neighbors, the SI over DI, where SI is the number of the exposed neighbors for individual I, DI is the degree of the total number of neighbors for the individual I. And also related to the covariance of the individual I. And the ZI, the covariance also follows the Bernoulli distribution with the probability is equal to 0.5. And BK, we assume it follows the normal distribution with mean of 0 and standard deviation of 0.5. And the beta alpha here is used to vary the effect size. After that, we can calculate the true spillover effect because we have the simulated all potential outcomes. Then we will estimate spillover effects and the corresponding variance using the IPW2 estimator. And after that, we will also calculate the word type 95% confidence interval. With this information, we can then calculate the power and the empirical coverage probabilities, which is ECP. And for each specific design parameters, we conduct a simulation with 500 repetitions. And the power was calculated by the number of the simulations that 95% confidence interval doesn't span 0, divided by the total number of the repetitions, which is 500. So here is the closed form expression derivation for the for the spillover effect. So I will just skip this. This is just some expression for calculate the power from the mathematically directly without a simulation. So here we went to the results. First, we found that the power didn't exhibit the monotonic change with an increase of the components, but it will increase with the more nodes or the large effect size. For example, if we increase the number of nodes, we can see there is an increase in the power in the y-axis. But when we vary the number of the components, we increase the number of components. The power don't have obvious monotrend for the either increase or decrease when we fix the number of the nodes. But if we don't fix the number of nodes, we fix the every component size. So when we increase the number of components, the number of nodes also increase. then we can see there's an increase in the power when we increase the number of components. So the second finding from this is we find that the impact of the number of components on the power is consistent when we use two different approach calculating the power. First is based on the simulation results, and the second one is based on the closed form expression we derived before. And the third one is about the node degree and transitivity. We found that power decreased with higher node degree or the higher transitivity with a fixed network size. And the last is the effect size on the power. We have two different setup with 10 components and 20 components. And yeah, we can say when there is a giant component in the network, then the power is pretty low. But when there's the nodes is more evenly distributed across the components, then we can see the power increase with higher effect size. And there are some limitations to the network. I'm not sure. It's just some limitations. The impact of the missing outcome will assume the missing completely at random, and also the approach depends on the FW2 estimator specifically, and we may need to generalize it in the further future. And also we want to use we want to do some further research to ascertain the precise connection between the power and simple size in the thermometric networks based studies, and here are some future work. I will just skip this for sorry. And here are selected reference. And thank you for your time and attention. I'm sorry about the a little bit time extra. And any questions?
Yeah, so Kurt, there is a question from Chalmers in the chat. Are there any considerations for MMAR designs and how they may be handled?
In this research, we don't actually consider about MMAR. We assume MCAR, but I think this is a good point. Maybe in the future we should look into it. But now we don't consider that for now.
So since Kurt is actually slightly over time, I think we might want to move on to the next presenter first, and then we can come back to your Q&A if there is extra time.
Okay, thank you very much.
Yeah, thank you, Kurt. And then the last presenter is Anisha Das from Florida State University. Hi, Anisha. And her work is about network detection in imaging genetics studies. So you can feel free to start.
Yeah, I think you can see my screen, right?
Yes.
Yeah, okay. So, okay. Good afternoon, everyone. Thank you for the nice introduction. And as my presentation title suggests, I'm going to talk about an approach for the detection of networks in imaging genetic studies. So this is a joint work with my advisors, Dr. Chao Wang and Dr. Ronji Liu. Here is a brief overview of the presentation. I'll start with a general introduction, then talk about the model development, followed by a brief simulation study, and then a real data example. So the main motivation behind the project is detection of the network or a connection among the significant genetic variants that affect the brain contour shape alterations, particularly among the patients who are affected with Alzheimer's. And by genetic variants, like we commonly refer to them as the single nucleotide polymorphisms or the SNPs. Now, when a patient is diagnosed with Alzheimer's, their brain gets shrunken, unlike the smoothness of the normal human brain. So here we shall mainly focus on two regions in the brain, the corpus callosum and the hippocampus. These two regions basically get significantly reduced among the Alzheimer's patients. Both of these regions are connected to memory. The corpus callosum happens to be the largest white matter structure in the brain, and the hippocampus is a part of the limbic system. So we will basically follow a three-tier process, starting with the functional data analysis framework for the detection of the genetic variants or the SNPs that significantly affect the human brain contour shape alterations. Then we will screen out the genetic variants related to the two-dimensional corpus callosum and the hippocampal shape responses or the phenotypes. And then we will develop a functional hybrid factor regression model, which will discover the network among the detected significant SNPs. So in this functional GWAS, we will follow a two-step procedure that involves a multivariate varying coefficient model followed by a global shear independence screening mechanism. So moving on with the methodology section, we first need to set up the representation of the elastic shape under a two-dimensional contour given the landmarks from the subcortical brain region. For this, we derive the normalized coordinate function via removal of shape-preserving transformations like rotation, scale, and translations from the landmarks. Shape-preserving as in, like, if you rotate the shape clockwise or anti-clockwise or change its axis or maybe rescale it, the shape won't undergo any change, but the original shape would be retained. So now accordingly, we define a square root velocity function representation shape for each subject. Now we start with n independent subjects and observe their subcortical brain structures, their genetic markers, the clinical covariates also. And now we consider S to be a grid point in a three-dimensional compact set, and H is a locus point in the set of all genetic markers. Now for the ith subject, we consider this Li to be a matrix with M landmarks that represent the contour of the subcortical brain region in an RT space. Now this YIS is a vector of imaging measurements which is observed at the point S. XI is a vector of clinical confounders. ZI particularly is a vector that represents the genetic, the associated genetic marker at the hth locus. We will incorporate this matrix W that will only hold the latent or the hidden factors. So now we obtain the functional shape responses from the linear Hilbert space and then run the multivariate varying coefficient model, which is as stated here. The model represents the genetic marker at the hth locus. Here S lies within 0 and 1. Now particularly this beta j is a vector that represents the non-genetic fixed effects, and alpha j is a vector of the genetic fixed effects. Now we want to test for the significance of the beta j's over here for each H and S. And we expect relatively small number of genetic markers to have significant causal association with imaging phenotypic measures or the imaging responses. And hence we are considering a global world type test statistic, which will eliminate the locus points that have weak or near zero genetic effect. Now, the top SNPs from this global shear independence screening test are passed on to define the association between the imaging responses and the covariates. So among covariates, we are considering both the observed SNPs and the hidden factors. And then we are defining this association through use of this model, which we specifically call the functional hybrid factor regression model. And here, instead of Z, we are using Z dash just to represent the top significant SNPs only. So when we want to estimate the coefficients here, we need to reparameterize the model, and then we obtain a reparameterized model as defined over here. Here, these columns of Z dash are expected to be orthogonal to those of the hidden factors. So now building the network. So basically this, we will now try to structure the multi-genome network among the detected significant genetic variants. So what we will do is, we find the correlation between one estimated confounder from this functional hybrid factor regression model in the previous step and all the SNPs, and then form a Latin square design matrix of this correlation estimates. So from there, we get the corresponding p-values as well, and we apply FDR correction on them. So now we choose some top SNPs, let's say top n star SNPs based on the FDR adjusted p-values. Then we arrange them again in a Latin square design matrix. Then we set up a second matrix that consists of zeros and ones. And how do we do that? We basically consider this criterion that if p-value is less than 0.05, we put 1, and otherwise we put a 0. So now in this way, we extract 2 cross 2 matrices, and then we note if there is a 0 or a 1 in the off-diagonal position. And in the diagonals, the number in the diagonals are expected to be 1 always. Now, once in both the off-diagonal position, that would imply a bidirectional connectivity, and 1, 0 and another 1 in the off-diagonal would imply a unidirectional connectivity. So what's that? Like, what's bidirectional? What's unidirectional? I'll come to that in a while. Now, moving on with the simulation study. So I'm not going into the simulation settings for the functional Jivas part, but I'm moving on with the setup for the network among the genetic variants, which might be associated with some variable of interest. So for this, what we do is we first simulate the SNP information, the genetic variance information, considering a set of conditional relationships. Now, specifically, we are considering a network which is known as the undirected graphical model or the Markov random field. So from there, we are creating a weighted version of the adjacency matrix. Then we take inverse of the matrix and set that partial correlation matrix as the true network. Then we are simulating the SNP information using this particular correlation structure. Okay, now from the specified functional Jivas model that I described in the methodology part, we are obtaining a certain number of significant genetic variants or SNPs. From there, we screen out 2000 SNPs, and through use of the hybrid factor regression model in the second part, we find the correlation between one randomly estimated confounder and all the remaining SNPs. Then this is how we extract these 2 cross 2 squares. So now, if both the first and the second row elements in the off-diagonal position has a 1, that implies a bidirectional connectivity. That means both the SNPs are connected to one another. Now, if the first row has a 1 and the second row has a 0 in the off-diagonal position, that implies the first SNP is connected to the second, but not the vice versa case. Again, if the first row has a 0 and the second row has a 1 in the off-diagonal, the second SNP is connected to the first one, but not vice versa. And of course, zeros in both the off-diagonal position, that would imply no connectivity. So in this way, we are noting down all the extracted squares. Then we find the number of bidirectional SNPs among those top 2000 significant SNPs that we are considering. So like basically, we are only noting down the the matrices of this form, the first row. So now from there, we do a connection mapping over here. So how we do that is we choose 2 SNPs as the most significant one and denote them using some separate colors. Here I used red and blue colors just to distinguish them from the remaining. So from this simulation, I obtained that there are 16 bidirectional SNPs. But what this implies is that it's not that all 16 of them are bidirectionally connected to the others. This implies that each one of them is bidirectionally connected with at least one of the remaining 15 SNPs. So now we find the correlation among the SNPs with bidirectional connectivity. So these structures are shown using heat maps. We show the correlation values along with the corresponding p-values. This is for the top 100 SNPs. So now, of course, lighter colors indicate a low value and intensity of colors increase with the increase in the magnitude. So here, if we look at the correlation map, some correlation values have extreme light colors that indicate a strong negative correlation. Now for p-values, the ones which are depicted in light colors that imply low p-values, which indicate stronger significance. Now, this was for the top 100 SNPs, like among those top 2000 SNPs, again, we treat, we consider the top 100 SNPs and do the connection mapping. So we repeated this same process using top 200 and top 500 SNPs as well. Then we also detected if the simulated correlation network happens to be a representation of the true network. For this, what we did is we performed the network comparison test. We set the null hypothesis as true network and simulated network are identical versus alternative that they are not identical. Now the test yields high p-values for all the cases when we consider the top 100, 200, and 500 significant SNPs. So high p-values, of course, lead us not to reject the null hypothesis. So we can conclude that the two networks happen to be identical. And now for better accuracy, we extracted confusion matrices by treating the networks as vectors. Here we calculated some metrics such as F1 score, recall, and precision. The accuracy also happens to be relatively high, and the corresponding p-values are relatively low over here. And if we look carefully, at least one of the three metrics that we calculated is above 90% for the three situations. So this also leads us to conclude that the predicted network based on this simulated results closely resemble the true network. So now moving on to the real data analysis part. We start with 707 subjects from the ATNI-1 study, the Alzheimer's Neuroimaging Initiative study. The free server tool is used to pre-process each of the T1 weighted MRI images, and we used these specialized packages to extract the shapes from the MRI images. For the hippocampus, we are particularly focusing the left hippocampus surface only. And further, we choose only those SNPs that form the genetic markers or those SNPs that have minor allele frequency greater than 0.05 are chosen. So first, we perform the principal component analysis on the SNP data and include the top two principal components as covariates along with age and gender when we are running the multivariate varying coefficient model. So here is a sample of the functional GWAS results. The table and the figures here are for the corpus callosum shape data only. Now, upon applying the global Sure independent screening procedure, the global wall type test statistic values are obtained for all the SNPs. Here, the results are tabulated in decreasing order of significance, which implies that the most significant SNP is placed at the top. Now, we set a sufficiently low level of significance and obtain around 2500 significant SNPs for the corpus callosum and around 3000 significant SNPs for the left hippocampus. So then we choose the top 100 SNPs under both the corpus callosum and the hippocampus settings to figure out if they have a bidirectional connectivity. For the top 100 SNPs, we obtain 9 SNPs that show bidirectional connectivity in the corpus callosum setup and 18 SNPs that show bidirectional connectivity in the hippocampus setup. So in the mapping, of course, we are considering the SNPs that are related to Alzheimer's as the most crucial and mark them using these blue colored symbols. We consider other neurodegenerative disorders to be the next most crucial and mark them using this red colored symbols. So here, instead of using the SNP names, we use the corresponding gene names to do the mapping. Now we set up the correlation structure using heat maps along with the corresponding p-values. This is for the corpus callosum shape contour. Here we observe 9 bidirectional SNPs among the top 100 SNPs, and from the map, it shows that most of them are significant as we observe considerably low p-values for a majority of them. And these are the heat maps that show the correlation structure and the p-values for the 18 SNPs with bidirectional connectivity. This is for the hippocampus surface, the left hippocampal surface. Here, not all of them look significant, as we can see there are multiple cells with moderately intense colors in the map for this p-values, of course, which indicate a higher p-value. But like if we look carefully, still a majority of them look significant. Okay, so this was all about my proposed model. So a few key takeaway points would be that we developed a shape on scalar functional regression model by adjusting for unknown latent confounders. A major challenge here was to tackle the heterogeneity among the shape images, and this has been taken care of by the functional hybrid factor regression model. Most importantly, this is a new attempt at determining the genetic variants that impact Alzheimer's through use of the network detection algorithm in a correlation structure. So here we made use of only 2 functional responses. So possible extension of the model can be to incorporate heterogeneity with more than 2 functional responses, or even include more number of SNPs that might impact a disease. And here are a few references I used. So I end my presentation here. Thank you all for attending. I would be happy to take any questions.
Are there any other questions from the audience? Thank you, Anisha, for your great presentation. I think it's time for a little break. And then all this session will continue until 1:30. Thank you.